So our next speaker is Charlie Weschler, who's an adjunct professor at Rutgers University in the Environmental and Occupational Health and Sciences Institute. He's also a visiting professor at the Danish Technical University and Tsinghua University, and a real leader in the subject of indoor chemistry. So I'll turn it over to Charlie and say hopefully we'll all feel the char.
Thank you, Rich. And thank you very much to the speakers who preceded me and set the stage and made it much easier for me to talk about the chemical composition of indoor PM. I'm going to begin with a very quick tour of some of the more important points we know regarding the composition of indoor PM. We'll begin by categorizing indoor PM as ultrafine particles, fine mode particles, and coarse mode particles. This categorization is useful when we talk about chemical composition. In the case of the ultrafine particles, as you've heard from the previous speaker, buildings do a reasonably good job of protecting us from outdoor ultrafine particles. So to a certain extent, the chemical constituents of indoor ultrafine particles come from indoor sources. Now, if we jump down to the coarse PM, particles larger than 2.5 microns, buildings do an even better job protecting us from coarse PM than they do from ultrafine particles. So again, the chemical constituents of coarse PM are chemicals that tend to have indoor sources. And in coarse PM, we see things like skin flakes and fibers and plastic wear particles. That leaves us with fine PM. And as you've already heard, outdoor fine PM can penetrate a building reasonably well. A significant fraction of outdoor fine PM is finding its way indoors. And at the same time, we have indoor sources of fine PM. So the chemical constituents of indoor fine PM, they have both outdoor and indoor sources. But if we compare the chemicals present in indoor fines to the chemicals present in outdoor fines, we find that indoor fines are enriched in chemicals from the occupants themselves, and they're also enriched in some of the additives that are used in the products that are part of our indoor environment. Phthalate plasticizers, organophosphates, brominated flame retardants, fluorinated surfactants. This pie chart shows the chemical composition of typical indoor fine PM. It's about 50% by weight organic carbon. Elemental carbon is just a very small piece of this pie, about 3%. Nitrate and sulfate together account for roughly 30% of the pie, and the counterions are ammonium and the hydronium ion. I'll speak about the water content separately in a moment. The water content is quite variable. About 1% of the pie, as I've drawn it here, I've labeled iron. Actually, if we sum all the transition metals found in indoor fine PM, they sum to about 1% of the pie by weight. And yet we want to pay attention to them because evidence suggests that the water-soluble TMs have a disproportionate effect on human health. So in terms of the transition metals, they're dominated by iron. Almost 70% of this 1% is iron. Zinc, about 10%. And then lesser amounts of vanadium, titanium, silver, copper, manganese, chromium. So back to water. The plot on the right shows the mass fraction of water increasing in outdoor PM as the relative humidity increases. Similar plots apply for indoor PM. So you see that below 25%, the water content is quite low. But between 50 and 70% relative humidity, the fine PM can be 10 to 40% water by weight. The water content depends on the chemical composition. It depends on the water-soluble salts. It depends on the oxidized organics. And of course, it depends on the relative humidity. Coarse PM contains less water than fine PM under the same relative humidity conditions because coarse PM contains less water-soluble salts and less oxidized organics. The water content is important. The water content influences the partitioning of gases, and it influences chemical reactions that occur in the aqueous phase. Barbara Turpin and her students are doing some very interesting work right now on chemical reactions that can occur in the aqueous phase indoors in aerosol particles. When we do have a significant amount of water associated with indoor PM, that water is likely coated by an organic film. There's substantial evidence for this. I mention it because the organic film can impact the transfer of gases into the PM and out of the PM. And the organic film can also impact partitioning. So with that quick background, let's talk about some emerging topics. And I'll begin with processes that change the chemical composition of indoor PM. Glenn has already spoken extensively about chemistry, including oxidation processes and acid-base chemistry. I'll say no more about the chemistry. I think Glenn has covered it more than adequately. What I'll focus on is partitioning of volatile species between the gas phase and the surface of airborne particles. And the partitioning occurs both for semi-volatile organic compounds, but also for inorganic species. The data I'm showing here is hot off the press. It's not yet appeared in the peer-reviewed literature. I thank Michael Waring for providing me with these two pie charts. He and his colleagues at Drexel obtained this information using an aerosol mass spectrometer. Glenn just spoke about AMS. And it's one of the first applications of AMS for indoor fine PM. They collected these PM at Drexel, on the campus of Drexel, and they simultaneously sampled outdoors and indoor PM at one of the Drexel buildings. So if we look, there's two slices of pie I'd like to focus on in this data. First, the slice of pie labeled HOA. HOA stands for hydrocarbon-like organic aerosols. What happens to the percentage of these hydrocarbon-like organic aerosols when we look at outdoors and compare to indoors PM? We see the HOA goes from 8% outdoors to almost 20% indoors. It more than doubles. Now, some of this reflects indoor particles that are rich in organic aerosols and generated indoors. But a large part of this increase in the HOA is due to partitioning. The indoor environment contains much higher concentrations of semi-volatile organic compounds than the outdoor environment. An outdoor particle comes indoors. It might lose something like PAHs, but it will acquire the phthalates and the organophosphates and the surfactants. The chemical composition of the outdoor PM changes significantly as it's transported indoors because of partitioning. And it does go both ways. So I mentioned it could lose PAHs. It can also lose something like ammonium nitrate. So you see in this example, the outdoor PM has a nitrate level of 11%. The indoor PM has an outdoor fraction of 4%. Ammonium nitrate associated with the outdoor particles is leaving that particle, those particles, as the particles are transported indoors. This was first pointed out by Melissa London in some wonderful studies she did in the middle of California, in the San Joaquin Valley. This is data that comes from Barb Turpin's group. Andrea Polidori was the lead author. The pie charts you see here are part of the RIOPA study, about 125 different homes, as I recall, and the homes were located in Los Angeles, Elizabeth, and Houston. So a little less than 50 homes in each of these cities represented here with these pie charts. And I'll focus just on the organic matter again. So that's the section of the pie marked OM. And we'll look at outdoors and indoors for the organic matter. So in the case of Los Angeles, outdoors, 29%, indoors, 48%. Elizabeth, New Jersey, outdoors, 30%, indoors, 54%. Houston, Texas, outdoor, 29%, indoor, 61%. A large reason, a significant amount of this increase is due to partitioning, to these outdoor PM acquiring SVOCs as it's transported indoors. Glenn mentioned the generation of secondary organic aerosols indoors. Secondary organic aerosols, when we increase the level of secondary organic aerosols indoors, we affect partitioning. When we increase the level of SVOCs indoors, the ratio of SVOCs associated with airborne particles to SVOCs in the gas phase, it goes up. And if we look at the math behind this, and this is the only equation I'm going to show in the presentation, but the ratio of an SVOC in the particle phase to the SVOC in the gas phase is given by, approximated by this expression. The concentration of airborne particles times the fraction of organic matter in the airborne particles times the octanol air partition coefficient divided by the density of the organic matter. I've circled the TSP, the airborne particles, and the fraction of organic matter because when SOA increases, both the TSP and the fraction of organic in airborne particles goes up. It's a double hit. So you're really having an impact on the partitioning of the SVOC when you increase SOA. And there's a number of chamber experiments that support this anticipation. The little figure on the right comes from a paper by Jennifer Benning, John Little, and colleagues. As you've heard, us, the occupants, we have a huge impact on indoor environments and on indoor PMs. We shed our entire outer layer of skin every 2 to 4 weeks. The shedding rate is enormous, 200 to 600,000 skin flakes a minute. The data on this slide comes from a classic study that appeared in Nature in 1973. Clark and Shirley, 2 British researchers, and they collected size-fractionated indoor PM from their homes, from a lab corridor, from the London Underground. And they analyzed the PM for squalene. And what they found was that the squalene content was between 40 and 100 micrograms per gram. Now, they use squalene, and I should mention, you've already heard from Glenn, squalene is a constituent of skin oil, about 10% skin oil by weight. And we, the occupants, are a relatively unique source of squalene. There are very few other sources of squalene in indoor environments. So you can use squalene as a marker of the occupants. And those skin flakes that we shed, they're about 1% squalene by weight. So Clark and Shirley used their squalene levels to argue that the airborne PM was about 1% skin flakes by weight. Now, since they did this study, there have been many other studies that have looked at the same question, and they basically support the observations of Clark and Shirley with substantial refinements. Microbes are present in indoor PM. You've already heard this. The data on the left comes from a study that has recently appeared in Indoor Air. It was conducted by researchers at Yale and Bill Nazaroff at UC Berkeley and colleagues in Korea. They measured indoor PM outdoor and indoor PM at 6 classrooms in 4 countries. And what you see in the box whisker plot on the left and the y-axis is different size ranges. You see that in the case of the bacteria, the mass fraction of bacteria associated with PM is higher indoors than outdoors. In the case of the fungi, the lower plot, you see that for fungi, the mass fraction of fungi tends to be higher outdoors than indoors. But the gap is closer than it was in the case of bacteria. The median mass fraction of bacteria in the indoor PM was 0.03%. The median mass fraction of fungi associated with the indoor PM was about an order of magnitude higher, 0.3%. Occupants, via their shedding and resuspension, contribute to these microbes found in indoor PM. Now, I mentioned that they collected PM both outdoors and indoors. They also collected PM when the classroom was occupied and when the classroom was empty. And it's quite interesting to look at the levels of these microbes in the PM when the classroom was occupied versus when it was empty. So in the case of bacteria, they found that when occupied, the level was about 80 times larger than when the classroom was empty. In the case of fungi, about 15 times larger when it was occupied, when they were occupied versus when they were empty. And in the case of PM, about 10 times larger. So you see how important the occupants are to the microbes associated with indoor PM. What we don't know, this work was based on gene sequence analysis. What we don't know is what fraction of these microbes are viable. There are literally thousands of organic molecules in indoor PM. The complexity is staggering when we think about the chemical composition of all these different molecules. However, if we look at the ratio of oxygen, I'm going to start differently here. If we look at the ratio of hydrogen to carbon in the PM and plot that ratio against the ratio of oxygen to carbon in the PM, the value we get tends to lie somewhere along the line you see in this plot on the left. This is called the Van Crevelen diagram. And the slope of this line is -1. So this is limiting, to some extent, the compositions we have to think about when we consider the organics in indoor PM. Now, I should make the point that this type of work has only been done to date with outdoor organics. It's not yet been done for indoor organics. Personally, I anticipate that we'll find something similar, but we won't really know until we perform a similar exercise for a large number of organic samples from different indoor environments. The composition of PM influences the uptake of gases into that PM and subsequent chemistry that can occur when gases are taken up by the PM. The example I have here is for dinitrogen pentoxide. It's from a relatively recent paper. The authors found that as the water content of PM increased, the accommodation coefficient, the uptake of N2O5 went up as much as a factor of 3. Conversely, the more nitrate present in the PM, the slower the uptake of the dinitrogen pentoxide. Now, this is just one example. Similar observations have been made for a number of gas phase species, and this applies whether we're talking about outdoors or indoors. The phase of indoor PM is also an important parameter to consider. PM can exist in the liquid phase, in the solid phase, in a glassy phase. We can have multiple phases in the same particle. We can have 2 different liquid phases in the same particle. Now, this is important because the phase that we're talking about affects partitioning, the rate of partitioning. It affects diffusion within the particle. Diffusion in a solid is about 10 to the 7th, can be 10 to the 7th times slower than diffusion in a liquid. It's going to affect chemistry that might occur in the PM. Okay, in the short time remaining, I'll say a little bit about what we need to know. And I warn you, this is highly personal. This is my own point of view in terms of what we need to know. And I'll start with transition metals, something I used to work with quite a bit. I showed near the beginning of the talk a pie chart for the transition metals present in indoor PM. We know remarkably little about the chemical form, the chemical speciation for those transition metals. I'll use iron as an example. The plots come from 2 studies by Oakes et al. At Georgia Tech. And in the plot at the top, the bars, and by the way, the x-axis are different sampling sites, urban and rural in Georgia. And this particular plot shows the amount of iron 2 present in the PM. The iron can be present primarily as either iron 2 or iron 3. Knowing the oxidation state of a transition metal is very important. the oxidation state really influences subsequent chemistry. So knowing that 25% of the iron is present as iron 2, very important. They also measured what fraction of the total iron was soluble. Again, this is important information. Water-soluble iron is certainly more bioavailable than iron hydroxide or aluminum iron oxides. And again, you see the importance of this. What I don't have on this slide, but should also be considered, is what are the ligands complexed to these various transition metals? If we're talking about iron 2, are the ligands primarily water? Or is it a mix of water and hydroxide ions? Do oxalate concentrations reach high enough levels that oxalate becomes an important ligand for the iron 2? So we really need more information on the nature of the transition metals, their speciation in indoor PM. It's not just enough to know what fraction of iron is there, what fraction of vanadium is there, what fraction of nickel. I've spoken about SVOCs sorbing to the surface of airborne particles. Imagine that we inhale a particle that has sorbed on its surface a phthalate ester. As that particle travels from the breathing zone to the alveoli, do those phthalate esters remain associated with the PM, or do they desorb? Well, the answer to this question depends on a comparison between the equilibration time and the residence time in various sections of the respiratory tract. Now, we know in turn that the equilibration time is going to depend on particle diameter and the partition coefficient. We've tried to do some modeling of this process. It's really complicated. It's really messy. All I can tell you at this point is we're fairly certain that for some SVOCs in some size ranges, they make it all the way to the alveoli. And for other SVOCs and in other size ranges, they're already desorbed fairly high up in the respiratory tract. As I said, the modeling is complicated, and experimental investigation, well, that's even more challenging. Glenn mentioned reactive oxygen species and showed some nice studies by Shahana. This plot also comes from one of Shahana's study. It's ROS indoors and outdoors in 8 different homes, Austin homes. The question I want to ask is, what role does ROS associated with PM, what role does that play in inducing oxidative stress? We know if we inhale PM that's enriched in certain transition metals, that PM will induce oxidative stress. Does ROS inherently associated with PM increase its potential to cause oxidative stress? A little work has been done on this using animal models, but I think it's still a question that remains. One quick point. Glenn mentioned the fact that SOA indoors tends to be fresh. SOA generated indoors tends to be fresh. This is important because studies from Phil Hopke's group indicate that the ROS from the ozone terpene chemistry is actually decaying over time, has a half-life of 6 or 7 hours. So the age of the PM matters, the age of the secondary organic aerosols, presumably, if we do want to pay attention to ROS. How does the phase of the PM affect partitioning? Today, when we estimate partitioning between SVOCs and airborne particles, we often use the octanol air partition coefficient. We're assuming that the phase is liquid. But what if the phase isn't liquid? And what if we're talking about a semi-solid or a glass? Well, then we're in gross error by estimating partitioning using this kind of approach. We're in gross error when we estimate timescales for certain partitioning processes to occur. For indoor PM, we simply don't know at this point how much of an issue or non-issue this is. So in summary, indoor PM are enriched in man-made organics and chemicals and microbes from occupants. As PM is transported from outdoors to indoors, the chemical change can be substantial. Partitioning can have a large impact on the composition of indoor PM and outdoor PM transported indoors. Phase state affects chemistry and partitioning. And my final point, and I'll return to what I was saying about transition metals a moment ago, we need better knowledge of the actual molecular nature of the chemicals present in indoor PM. I mentioned this in terms of transition metal complexes, but it also is true for some of the organic species. And I think a large number of people are unaware of the holes in our knowledge when it comes to the chemical composition of indoor PM. So with that, thanks for your attention.